All right, so last section in this unit. Problems with elevators. So I'm assuming all of you have been in an elevator at some point in your life. Have any of you ever done, I've done this lots. I don't know if you've done this. Whenever you are going up in an elevator, right before it comes to a stop, have you ever jumped?
Yes.
How does it feel?
Weird.
You feel like you're jumping higher, right?
Yeah.
Or if you're going down and you get to the bottom floor, if you jump, what happens?
You don't bump your head.
You don't bump your head. Yeah, you feel like you're falling faster, right? You're going to hit the ground quicker.
Because it feels like it goes down and then you both fall.
Yeah, exactly. It has to do with that. It's like if you've ever been on rides at a amusement park, either they do the drop or they do the thing where they launch you up in the air and then pull you back down. Yeah, the ones where it's like they're nice and slow, they're slowly lifting you up, they give you the nice feeling of, oh, you got a nice view of the whole city, and then they all of a sudden drop you. Similar to that, yeah. So that's the type of problem we're dealing with today. So, Mahmoud. So we do have 18 minutes till lunch. I'm hoping we can finish it off in those 18 minutes. Thank you. So as you are accelerating upwards or downwards, you might feel like you are feeling heavier or lighter. And this has to do with forces. Since we're dealing with this in dynamics, this is going to change depending on if you're accelerating up or down. So you have an actual weight, which is the force of gravity. That's not going to change if you're in an elevator, because you're not really changing enough in height. That's always going to be mass times acceleration due to gravity. However, your apparent weight changes. Your apparent weight is the weight that you feel. The apparent weight, or this amount that you feel, is really the normal force. So the weight that you're feeling now as you're sitting down is because of the normal force pushing you up. That's what gives you that feeling that you have weight. So if there's no normal force, you feel like you're weightless. Or if your normal force is somehow bigger because the ground's pushing you up, you're going to feel different than if you're just sitting normally. So this is what's going to happen if we're dealing with our elevators. Is this in your notes?
No.
The student jumping off the desk?
No. Yes. No.
What's the next box that shows it? Okay. Wait, let me pull out mass plus spring. I have it here. Describe 2 times when mass appears heavier than normal. Okay. So I'm going to ignore what's on here for a sec, and we'll just go with what's in your notes. So when you're in an elevator, think about when you've been in an elevator. 1 or 2 times you feel heavier in that elevator.
When you're going up, look.
Well, both is right, but there's a certain circumstance. When you're going up, and what happens? No, not when you stop. When you're going up from rest. So in the first box, I'll just do it on here. In the first box, it's when you are going up from rest.
So the first number 1.
Yeah, so this is under the describe 2 times when the mass appears heavier than normal. In the box where it says describe 2 times when the mass appears heavier, this is the first one. What's the second one? We're talking about in an elevator. Going down. and
Stop.
stopping. Going down and stopping. So you can try this next time you're in the elevator, because I know you all carry around your notes with you all the time.
Newton's first law.
It is Newton's first law.
No, it's second.
So you can, if you really want to, if you have an elevator in your house or in your apartment building that you're in, you can give this a try. Next time you go to CFC or something like that, you can try this out. So this is when you experience like you are heavier. And when we're thinking about this, this is when we're accelerating upwards. So underneath it says, what can you summarize about the acceleration of the mass? This means that our acceleration is upwards. I just didn't feel like writing acceleration, but it's upwards. And I'll draw a free body diagram of this so you can see it. Right beside that, it's going to be, when do we feel lighter?
When,
It's going to be the opposite of this.
yeah, when you're stopping. When you're stopping.
So going up
Stopping, you're going up.
and you stop, or
Going down. You start going down from
going down from rest. And what can you summarize about my acceleration in this case?
our acceleration is down.
Yeah. So acceleration downwards. No, that's the student jumping from a desk. Don't worry about the notes. I'm just filling in what's on your set of notes because I like those better. And there are 3 times. Because this is a special case. Yeah. This does happen in other things, but guaranteed you're on an elevator more than you're in a plane, or more than you're at a roller coaster, or more than you're at an amusement park on different other things. So this occurs more often than the others. That's why we specifically talk about this.
Is it when you're going up and the constant velocity, going down and velocity when you're not moving?
There you go. Yeah. So up
And our acceleration is constant.
at constant velocity. Going down. Can't spell constant there. Constant velocity or at rest. Then don't move. Then don't move. Right.
Acceleration is constant.
Acceleration is 0. So these are the 3 different cases, and surprisingly, underneath that, we're going to talk about 3 different situations. So again, just like I've told you with all of the F-net equations that we've ever done, don't memorize. Memorizing equations is not going to help you. Nope. The F-net equation is not on the formula sheet. Like, as in the sum of the forces is never on the formula sheet. So sometimes it's tension minus force of gravity, sometimes it's force of gravity minus tension. Sometimes it's force of applied minus force of friction, sometimes it's force of friction minus force applied. So don't bother memorizing, it won't help. All right, everyone's got this written out?
Yes.
Okay, so I'm going to skip through this. We'll get to the example. Okay, is this the same one you have? Example 1, 65 kilogram person in an elevator traveling upwards at 5 meters per second. Perfect. Okay, good. We're back on track. So, what does my free body diagram look like in this case? You absolutely need to go to the bathroom at this point. That you need to announce it without putting up your hand. Still need to go? You can go, yes. So, what forces do I have on a person in an elevator? Force of gravity. Tension. This person's not dangling by a rope. Yes, but we're talking about the person, not the elevator. The normal force. And which force is bigger, normal or force of gravity? Person in the elevator is traveling upwards. So because he's moving upwards, the normal or the force normal should be bigger, right? There's no applied force. So think about the person. What forces are acting on the person? Force of gravity is pulling the person down. The floor of the elevator is pushing him up. So it's normal force. I should have everyone screaming at me right now.
What?
I should have everybody screaming at me right now. Something is wrong. I just made one of the most common mistakes that I will ever see on a test. That's why I did it. This is why I'm making you think about it, so that next time that you see it, you'll be able to recognize it. Does a force, or just because you are moving upwards, does that mean the force upwards is bigger? How can you tell if a force is bigger? If they're accelerating. Am I accelerating? 5 meters per second. Is this a unit for acceleration? This is a constant velocity. Acceleration is 0, yes. I turned it into a trick question because I didn't point it out. So, these two must be equal. I didn't draw them equal, but they should be equal. So, this is confusing because I can word this the exact same way. Put a squared here. Now it's a bigger force upwards. So, by a single 2, I can mess you up.
Wow.
So this is why I'm pointing this out, because it's going to come. Be very, very afraid of it, because it's going to come. So you need to be aware. Am I accelerating? Am I not? So since these two are equal, can someone remind me, what is apparent weight? If I'm solving for apparent weight, which of these two is apparent weight? Check your notes. It's further up the notes. Normal force. So if I want apparent weight, I'm looking for the normal force. So in this case, normal force is my force of gravity. So in order to solve it, I just do mass times 9.8. I have the mass, 65. I have the acceleration due to gravity, because we're not told we're anywhere other than Earth. So we get a rounded number of 640 newtons. Hopefully, then I'll change this number. So, in this case, I'll get to your question, just hang on a sec. So in this case, since my acceleration is 0, then F net is 0. Because F net is 0, my up and down forces are equal. I even had this written out on the board when I asked you about what's wrong with this question. Yes, you had a question. We'll get to that. Later question. Any other questions with this? For those of you who love your lunch period, let's just whip through these other two, because I'm also hungry. So this same person is now in an elevator that accelerates upwards. Now it's being nice. It's going to tell you we want the apparent force. So if it's accelerating upwards, normal force is bigger than force of gravity. So therefore, I should not memorize the F net equation.
It's good.
I would hate to be the single person who continues to talk and would cause the entire class to stay in at lunch.
It's not equal.
No, it's not fair. I completely 100% agree with you. That is not fair that the entire class has to wait for a single individual who decides that he wants to be selfish and take up the entire time and talk instead of allowing the rest of the class to learn. That is not fair. I am 100% with you. The equation's not fair?
They are not equal. Right?
Correct, they're not equal because we're accelerating. So then what's my F net equation? Yeah. Larger force minus smaller force. And now we go about solving this. So mass times acceleration equals the normal force, which is what we're looking for, minus mg. And then just solve for Fn. So Fn equals ma plus mg. I have the mass. I know the acceleration. And then calculate it. So 960. So in a case when you're accelerating upwards, you should feel heavier. And this is heavier than my force of gravity. So this makes sense. So the nice thing about this is even though my F net changes, intuitively you can think about this. And you can try and figure out something's wrong. Is there something to say when the net... is there a blank for you to fill in, or is this already written there? When the net for... doesn't matter. Let's do the last one. So now we're reaching the top floor and we're decelerating. So we're slowing down. So this means Fg is bigger.
Yeah. The same equation. Let's go. Fg minus Fn.
Equals this. F net is ma, Fg is mg, minus force of friction, plug in numbers. We're still 65 kilograms. We haven't changed mass, hopefully. So when I solve for Fn, I will add this onto this side, subtract all this onto this side, so you'll get 320 newtons. We're assuming it's the same person on the same elevator. So I'm not going to do the last little box at the bottom. So this, again, makes sense. Shh. I haven't finished yet. I haven't finished yet. This means you shouldn't be packing up yet. Noor, Miriam, have a seat. Kareem's, have a seat. So, again, intuitively, the force of gravity is bigger than my normal force, meaning if my normal force is smaller, I feel lighter. So this is going to be the case. So these are nice. You can just think about it at the end of solving it. You can figure out, is that correct or not? Okay, so I'm done.